All right, the first page here is simply nomenclature. Now, at the start of chapter 10, I think we did a review of nomenclature of alkyl halides, and that's what this is. It's a alkyl halides with mixed functionality and stuff like that. Starting out with our first one, this is obviously an alkene. It's going to be a 1, 2, 3, 4. So it's a butene.
One bromo.
We're going to have 1 bromo. It's going to be a 2 ene and a 3 methyl. 1 bromo, 3 methyl, 2 butene. The next guy is an alkyne, where we remember with alkynes, we want to, alkynes and alkenes, want to give the double bond the lowest number possible. So we're going to start numbering here. It's going to be a butyne, 4 carbons. It's going to be a 1 butyne, and there's going to be a 3 fluoro. This is also a 1, 2, 3, 4. It's also a butyne, but we have a chiral center here. So we have to do R and S. This obviously is going to be carbon number 1. As we look at our chiral center, the bromine is going to be number 1. Our triple bond here, bonded to 3 carbons, that's going to be number 2. And our methyl is number 3. Hydrogen is in the back. And we are going clockwise. That makes it R, 3 bromo, 1 butyne.
You don't have to name it as 3R because it's on the 3rd carbon.
No. And finally, our last guy is going to be a cyclohexane. We have 2 chiral centers we have to deal with. This is going to be carbon number 1 because it's a bromo. Carbon 2, we have a methyl. Now looking here at carbon 1, our highest priority is going to be the bromine. Up here, we are attached around the ring to carbons, which beats out this guy, which is only attached to the ring, but also to a methyl, and hydrogen's out here. So we're going this way. That's S for our top carbon. Our bottom carbon, our highest priority is going to be this guy because it's linked to a bromine. We're going to go this way, back through the ring. Our methyl group is here. That makes it S. Wait a minute.
You said to not put
Yeah,
RS.
It says do not.
Did I do it backwards here? I'm feeling better today, but I'm still standing awfully close to this. I believe this is the proper name. 1R, 2R, 3-methyl, or 2-methyl cyclohexane. I might have reversed my numbers here. I'm sorry.
You told us to not.
You said don't include RS.
I'm sorry?
You said don't put in RS.
Oh yeah, that's what's on the page?
Yeah.
Yeah, it
Oh.
says do not.
Okay, that wasn't supposed to be there.
All right, I have a question about the 3rd.
Yeah.
one.
This guy?
Yeah, is that not a methyl?
Yeah, this is a methyl.
So why is that not included in the nomenclature?
It is 1, 2, 3, 4, so it's a butte.
It's number 3 for the.
Oh.
It's all part of a chain, yeah.
Okay.
I think I'm confused with the first one. I thought we were supposed to start and go through the double bond and origin off.
That's only if you have a double bond in a ring,
Only the ring.
only in a ring.
So, okay.
Otherwise, you would give the double bond the lowest possible number. Here it would be carbon 2 in either case, so we go lowest number, first point of difference, and that's the bromine there.
But on here, we're doing alphabetically, right, because of the
Right.
allergen?
Yeah.
All right. Again, a very simple thing. This is going to be a pentane. We're going to have a bromine and carbon 2, so we'll start here. Carbon 2, we need a bromine. Carbon 3, we need a chlorine. And carbon 4, we need a methyl. This guy here, 1-chloro-4-methyl, 1-pentine. So we're going to have an alkyne. We have a parent with 5 carbons. So we'll start here to give the alkyne the lowest number. 1, 2, 3, 4, 5. There's our pentine. In carbon 1, we have a chlorine. In carbon 4, we have a methyl. And I think that's it. Any questions? The exam will also have 6 simple nomenclatures, very similar to these guys. Mixed functionality with alkyl halides.
Just, the NBS light, that makes it just a regular.
All right, next we have a bunch of fairly simple substitution and elimination reactions. Also a couple radical reactions. We look at our first one. We have cyclohexene. Our reactants here are n-bromosuccinimide, light, and carbon 10 as a solvent. We should immediately recognize that NBS in light is going to generate bromine radicals. This is an alkene. These guys here are the allylic positions. Remember, in an alkene, allylic positions are very reactive, very stable radicals, and so we get selective bromination at either here or here. This is simply going to give us the bromoalkene. Once again, in the allylic position, here or here. Our second one is an E2 elimination. With an E2 elimination, we have to remember we're going to make an alkene. It's going to be a concerted reaction. We're going to lose HBr, and we're going to form the most highly substituted alkene. Finally, the hydrogen and the bromine must be trans to each other. So if we look at our drawing here, our bromine here is trans to this ethyl group. That won't work. We're going to have to rotate either this carbon or this carbon. I rotated the front one. I'll go back just so you can see what I did. All I'm doing is moving the ethyl down, hydrogen up. Again, our hydrogen is now trans to our bromine. Our elimination is going to proceed this way. As you look at this in the sawhorse projection, you can easily see that the 2 methyl groups are on opposite sides. Therefore, the product that we would get would look like this with our 2 methyls trans. Now, our true stereochemistry here is this, because it's along the chain. So this is going to be cis, so it's Z stereochemistry. Our next guy here, we're using an amine as a nucleophile in a simple SN2 reaction. The nitrogen with its lone pair is going to attack this carbon. Again, because it's SN2, there is no carbocation intermediate. It's a nice, simple, concerted reaction. Nucleophile attacks, leaving group leaves. Initially, we're going to form an ammonium ion, aren't we? Because we'll have an extra nitrogen, a hydrogen on the nitrogen. But we're going to lose that, and we're going to form the simple neutral amine. Now, if you had drawn this as NH2, that would be fine. You put NH2 positive, but typically we want to lose that hydrogen in the reaction conditions to get the neutral amine. Again, all we do is substitute the nitrogen for where the bromine is. I believe your paper shows this also as SN2. And again, this is an allylic bromide, isn't it? Allylic and benzylic bromides are very reactive in terms of SN2 reactions. Very nice reaction. All that happens is the oxyanion will displace the bromine, and we will make the ether. Any questions? All right, this reaction, I said we're going to do it under E1 conditions. That should tell you that we're going to make a carbocation. I also want you to realize that this is going to involve a 1,2 hydride shift. Now, in an E1 elimination, first thing we're going to do is lose the bromine. That's our slow step. That's why it's unimolecular. The bromine comes off and will form a carbocation at this center. That's our initially formed carbocation. Now this is a secondary carbocation, but it's adjacent to a tertiary center. So because of that, we're going to undergo our 1,2 hydride shift. This hydrogen will slide over from here to here, and we'll be left with a tertiary carbocation. Finally, in the fast step of the reaction, water is going to attack as our nucleophile, going to convert this to the alcohol. Once again, methoxide in an SN2 reaction. Here we have a chiral center, don't we? So when you notice that, you should say to yourself, because this is an SN2 reaction, we're going to have inversion of configuration at our chiral center. This is hydrogen back, bromine forward. We're going to have backside attack by our oxyanion, and we'll wind up with this, methoxide back, hydrogen forward. Simply invert the stereochemistry at this center. I put the structure of azide ion here, just to remind you of what it looks like. Remember, it's a structure we can draw resonance forms. We did that back in chapter 3. Right now, all we need to do is realize that azide anion is a very nice nucleophile. Very simple alkyl halide here. Nitrogen is going to attack. Bromine will leave. SN2 reaction. And we wind up with the alkyl azide. If you wanted to draw the whole thing out, you could. Don't have to. Any questions on these three? Yeah.
Could you go over the top one more time?
The top one. Okay. Well, we're going to have to go back to the whole story. Step 1. It's an E1 reaction. So the bromine leaves. That's our slow step. And that gives us the secondary carbocation. Okay. This is adjacent to a tertiary center. Because it's adjacent to the tertiary center, this would be a more stable carbocation. So that's why you do your 1,2 hydride shift here. The hydrogen with its pair of electrons will simply move from here up to here to leave us with the tertiary carbocation. Now we're doing this in water, so water is going to be our nucleophile. So the oxygen will attach here, and we'll wind up with the tertiary alcohol. Any other questions? Another set of 4. Once again, methoxide is nucleophile, SN2 reaction, allylic bromide, made this, our very first one. This attacks, this leaves, we simply make the ether. We are doing a E2 elimination here. Remember, E2 elimination is conservative. So we do not have a carbocation, we do not have rearrangement. Because of that, our double bond is going to form between these carbons or these, same thing. We're simply going to lose HBr and make the alkene. This is just the opposite of the reaction we saw on the previous slide. Here we have our nitrogen nucleophile on this side, and this is bromomethane. Nitrogen is going to attack, bromine will leave, we will lose a proton from this, and simply wind up with the N-ethylamine. Once again, if you would have left the hydrogen on here, that would have been fine if you would have shown it with a positive charge. 4 things on nitrogen is positive. And bromosuccinimide. Once again, this tells us we are doing free radical bromination. We look at our compound here. This carbon right here is both allylic, that is adjacent to the double bond, and it's benzylic. So it's a winner twice over. Very, very reactive at this carbon. All we're going to do is add bromine radical here to get this as our structure. Any question on this set? Yeah.
For the second SN2 problem, I'm not sure how that nitrogen attacks.
Oh, here?
Yeah.
Because
of,
remember, we have a lone pair here, right here.
Okay.
This is going to attack the CH2, bromine leaves, and we have a CH2, CH3 now attached directly to the nitrogen.
So we're just not showing the hydrogen attached
Right.
in the...
Because the hydrogen is there initially, but you lose that at equilibrium.
Okay. So that for the answer, the nitrogen, should that be like a cation?
Yeah, if you kept the hydrogen, that would be fine,
Okay.
but you would have to show it with positive charge. 4 things on nitrogen, positive charge. All right, once again, we're doing a simple E2 elimination. We are going to form the most highly substituted alkene. So we're not going to eliminate going up this way. We're going to eliminate going down this way. There are two possible products you could get because there are two hydrogens here. You could pull off either one. You would either get this, the cis isomer, or the trans isomer. Either one would be fine. Once again, there are two hydrogens here, so you can get either cis or trans. Methoxide, SN2, allylic bromide. Simply displace the bromine at this point and make the ether. And this last one, of course, is cute. Here we have a compound that has the nucleophilic oxyanion and our leaving group in the same molecule. We put this in DMSO, that favors SN2 reactions, and all the world that's going to happen is the oxyanion is going to reach around, it's going to attack this carbon, bromine will leave, and we'll wind up with a ring. The ring will have an oxygen and 1, 2, 3, 4 carbons, and it's simply tetrahydrofuran. You could potentially link these guys together, couldn't you? One molecule could attack the other. Whenever you have an intramolecular reaction like this to form a nice sized ring, that takes precedence, usually by about a factor of 1 million or so. The entropy effect drives this reaction as opposed to the intermolecular. Any questions? All right, your exam will also have 14 similar reactions, again, substitutions, eliminations, whatever. All right, very simple lesson, one reaction here. The format here was to draw the initially formed carbocation, the most stable carbocation following rearrangement, and the final product. Now we know if we're going to do an SN1 reaction, the first thing that's going to happen is this bromine is going to come off, and our initially formed carbocation is therefore going to be our secondary carbocation, looking like that. Now I put the hydrogen in just to make it easy to see, because our most stable carbocation following rearrangement is going to be at our tertiary center. So once again, we have a secondary carbocation adjacent to a tertiary carbon. That means that this hydrogen is going to slip over with its electrons to this center, and we're going to leave the tertiary carbocation. That is our most stable following rearrangement. Finally, we have methoxide as a nucleophile. Methoxide in the fast step now, the oxygen will attack the carbocation, and we will get the ether as our product. Any questions? All right, this again is an exercise in E2 eliminations. In our E2 elimination, we remember the bromine, that is our leaving group, and the hydrogen must be trans to each other. Once again, I've drawn this thing in a simple sawhorse configuration. Our bromine is actually trans to a methyl. So let's go ahead and rotate this back bromine carbon. Bring our bromine down. So it used to be up, we're going to bring it down with the methyl group over here. And we wind up with this and this, coplanar and trans. This only gives one product when the elimination occurs. So we're going to pull the hydrogen off here, the bromine's going to leave. The product is going to be the trans methyl groups, cis with the longest chain. And the explanation as to why, all the world you would have to say is the elimination must be trans, or you could also use the word anterifation. Any questions? All right, just for comic relief, I also threw in some multiple choice questions. And your exam will also have comparable multiple choice questions. What's true regarding this compound? It will be very unreactive in an SN2 reaction. Well, remember, for an SN2 reaction, we have to be able to get at this carbon, don't we? We've got these big tert-butyl groups on both sides blocking it. Because of that, it's going to be very, very difficult for a nucleophile to get in here, backside, and displace the bromine. So it is very unreactive in SN2. It will readily undergo an E2 elimination. Well, point to the hydrogen that you would pull off here. There are only methyl groups on both adjacent carbons, so no, it cannot undergo E2. C, it will be very reactive in SN1 reactions. Well, this is a secondary carbocation, isn't it? Very crowded. Lots of good reasons for this bromine just to want to leave. Once it left, it would probably rearrange, but yes, it will be reactive in SN1 because it's a nice, stable carbocation. A and C, A, B, and C, obviously, SN2, SN1, that's the proper answer. All right, if we made a carbocation here, what would happen to it? Would it undergo a 1,2 hydride transfer? Once again, there is no hydrogen on either carbon to transfer, is there? So, no hydride. It would undergo a 1,2 methyl transfer. Remember, once we have a carbocation here, just like a hydride can shift over, if you don't have a hydrogen, the methyl group is the next lightest thing, and it can actually just simply slide from here to here to make the product. So yeah, that's a good one. Rapidly undergo E2 elimination. No, it can't. There's no hydrogen. This is our carbocation. Once we do our methyl transfer, we would have this. Therefore, this is the proper answer.
Would there still be the?
There should be a
cation?
positive charge here. I left that off. In both SN1 and E1, there is an intermediate carbocation. Absolutely. They both involve the same intermediate. Leaving groups that are strong bases will favor the reaction. Actually, that's not true, is it? We want a leaving group that is a strong acid, not a strong base. Strong acid leaving group works very well. Polar solvents will promote ionization. Sure, you're making ions. You want something polar. Once again, A and C are correct. Simple nomenclature here. What is the role of methoxide? Is it the electrophile, the nucleophile, the leaving group, or the solvent? Well, it's clearly not the solvent. Clearly not the leaving group. This thing is a negative charge and it's looking for something positive. That makes it the nucleophile. All right, this one was cute. Here's our same reaction. How would you make this? We could take cyclohexene, bromine, and light. Bromine and light does what?
Free radical.
Makes bromine radicals. This is an allylic bromide. That'll work well. Bromination of cyclohexene using HBr peroxide. Well, that's radical too, but that adds to our double bond, doesn't it? Bromination using NBS and light. Yep, that one works. Again, allylic, cyclohexene, A and C only are correct.
Wouldn't A give you a radical though?
Yeah, but again, we have an alkene. This is our allylic position, the bromine radical. Same bromine radical you get with NBS. NBS is just a little nicer to use than bromine itself. If we did an E2 elimination here, would the carbocation intermediate rearrange? No, of course not. There is no carbocation in an E2. Bromine radical would be the leaving group. Well, that's silly. Bromine radicals don't leave. The conjugated diene, that is 1,3-cyclohexadiene, would be formed. So we're going to eliminate across here. That's right. The other two aren't. This is our best answer. All right, very simple, very, very simple two-step synthesis. Remember, when you're going to do a synthesis, you start with your final product and you ask yourself questions. You're allowed to take a peek at your starting material, but remember, you want to work backwards. First thing you would do is look at our product here. You say, well, what is it? It's an alkyl bromide. The bromine is attached to the secondary carbon. How many ways do you know to make alkyl bromides with the bromine attached to the carbon that would give the most stable carbocation. That is marconic. You know one. That's the addition of HBr to an alkene. So you look at this and you say, alkyl halide, Markovnikov regiochemistry. You could do this if you had an alkene and you simply added HBr. The alkene should have 3 carbons, and one of these is a double bond. HBr are our reactants, and the alkene would look like this. Simple Markovnikov reaction. Now you look at your next intermediate in line, and you ask yourself the same questions. What is it? How do I know to make it? It's an alkene. I know 2 ways to make alkenes, don't I? I can do an elimination reaction, or I can take an alkyne and do a partial reduction. Only 2 ways we know to make an alkene. Since we're starting with an alkyne, obviously we want to do a partial reduction. Partial reduction conditions, we know 2. We can use hydrogen with Lindlar catalyst. Remember, Lindlar stands for lousy, so you just add 1. We can also do dissolving metal, that's sodium or lithium and liquid ammonia. Lindlar is probably much easier here. There's no stereochemistry to worry about. I would just use Lindlar. You could have used either. Remember, if you would have used hydrogen and platinum, this would have gone all the way to the alkane. So you can't do that. Any questions? All right, the last question was extra credit. And it simply has to do with, from chapter 10, the free radical halogenation sequence. What I asked was for you to give the initiation step for the chlorination of methane, full propagation sequence, and the termination step, any termination step of the reaction. Propagation is very simple. We have chlorine and we have light. What's going to happen is light is going to split the chlorine-chlorine bond. We're going to make 2 radicals like this. This is our initiation step. The propagation step. In propagation, we need to start with one of these chlorine radicals. That must react with methane to give a methane radical. That must in turn react with chlorine to reform the chlorine radical and to give the product. Remember, you must start off with a chlorine radical and end up with a chlorine radical. That makes it a chain reaction. So the propagation would look like this. Here's our starting radical, here's our ending radical. It must be the same. Chlorine radical holds off a hydrogen to give the methyl radical. This then reacts with another mole of chlorine, splits our bond, we form the chlorine radical and chloromethane as our product. To get full credit, you would have to show the full propagation sequence And again, make sure you start with a radical and end up with one. And finally, termination. Termination, because the chain reaction requires a radical, all you do in termination is get rid of the radical. You can get rid of the radical, at least 3 ways. 2 chlorine radicals get recombined to give chlorine. Chlorine and a methyl radical could combine to give this. 2 methyl radicals could combine to make ethane.
So which was more likely to happen?
Well, which is more likely? That would actually depend on your concentrations. If you had a high concentration of chlorine, this is probably the most likely process. That's because methyl radicals are so unstable that they'll react rapidly with Cl2. These guys hang around long enough to find each other. So, this is just the reverse of the initiation step. So this goes back and forth, and then you get products trickling out. The full sequence: initiation, propagation, and termination look like this. All right, your exam will also have basically every style question that we have here, including an extra credit. I think it comes to a total of 109 points. There will be no E3 extra credit after this one, because this only covers 2 chapters, and I expect everyone to do very, very well. Right? Okay, if anyone has any more questions, we can sit and talk. Or you can go, whatever you like to do.
Are we able to use a note card this time?
Oh yeah, you can bring a note card. You can actually bring, 3 note cards if you wanted to. By now you don't need to.
When a reaction is like uncertain, does it give like the propagation?